Good morning, students. Myself, Vijay Shankar from ECE Department, Chevrolet Engineering College. Today, we are going to discuss about some more examples in the Magneto static studies put in it. The first example is a conductor 1 centimeters length. A conductor of 1 centimeter length is parallel to the z-axis. Hence, it is also in the z-axis only. Is parallel to the z-axis and rotates at radius of R is equal to, consider it is L is equal to 1 centimeter. R is equal to 25 centimeters at 1200 RPM, revolution per minute. Find the induced voltage. So you can find out the induced voltage if the radial field is given by the B bar is equal to given 0.5 AR bar, that is a Weber per meter square, that is Tesla. These are the given data. The length of the conductor is given 1 centimeters. That is in the z-axis is parallel, and the rotates of 25 centimeters at 1200 RPM. You have to find out the induced voltage if the radial field is given of the B bar is equal to 0.5 AR bar in Tesla. So to find the induced EMF, E is equal to integral E bar dot dl bar. E bar dot dl bar. Given the B bar, we need to find using this data. E bar is equal to, given the RPM, V bar the velocity, cross magnetic flux is given, the P bar is equal to 0.5 AR in AR bar. Here V bar is a linear velocity. See, in this, the V bar is equal to, what is the V bar is equal to now? The V bar is equal to the given the length 1 centimeter and R is at 225 centimeters at 1200 RPM minutes. So 1 minute there are a 1200 revolution, which is corresponds 20 revolution in 1 second. So the minutes we can convert into the seconds, 20 revolutions in 1 second. 1 revolution distance traveled is at 2 pi r meter. 1 revolution distance traveled in the 2 pi r meter as the 20 revolutions. Means in the second, 1 second is 20 revolution. 1 minute, they given the revolution per minute, there are 1200 revolution. In 1 second, the 20 revolutions. And 1 revolution distance travel is at 2 pi r meter. Hence, the 20 revolution distance travel in 1 second. In 1 second. So in 1 second, there is a 20 into 2 pi r. So 20 into 2 pi r is a 40 into pi r. What is the R given? The 25 centimeters. The conductor rotates the phi direction as the linear velocity is given by R. R you can convert into the meters. So 40 into pi, 25 into 10 to the power of minus 2. 25 into 10 to the power of minus 2, that is equal to 25 into 40 is 1000 pi into 10 to the power of minus 2. Because it is in the velocity is in the phi direction, so A phi bar, V bar is equal to revolution per minute means it is a phi direction, the 360 degrees. So V bar is equal to 1000 pi into 10 to the power of minus 2 A phi bar. Or it is 10 to the power of minus 2, you can remove here the 10 pi into EA5 bar. The revolution V bar is equal to, okay, the 10 pi. Pi is a 3.14 actually. It is multiplied is into 10 means 31.416 A5 bar. The velocity is a meters per second. Got it, my students. So we got the E bar is equal to V bar is equal to. Now we can substitute the E bar is equal to V bar as a 331.416 A5 bar. The cross product with the, what is the V bar given? 0.5 into AR. 0.5 into AR bar. Okay. That is equal to 31.4 into 0.5. 31.4 into 0.5. 31, my dear students. A5 and AR. A5 bar cross AR bar. So actually, the products are phi and the Z. If you consider the cylindrical coordinate system, R phi, the cross product is a Z. And if it is the reverse here, phi cross AR is a negative value, 31.14 into 0.5, nothing but is a 1/2 AZ bar. AZ bar. It is around of 15.7 is a 1/4. So that is equal to minus 15.7 AZ bar. Okay, we got the E bar is equal. We need to find the induced voltage. What is the induced voltage? E bar is equal to integral electric field plus the DL bar. E is equal to, what is the electric field here? We got a minus 15.7 AZ bar dot DL bar. DL bar means it is in the parallel to the Z axis of the conductor. 1 centimeter is parallel to the Z axis. So DL bar is equal to, along it is a Z axis, DL bar is equal to DZ into AZ bar. DZ into AZ bar. So you can write this as a function of DZ into AZ bar. Integral minus 15.7 AZ bar dot AZ bar is equal to 1. So DZ. What is the Z here? Z is parallel to the conductor is 1 centimeter. Means Z is starts at the 0. And centimeters, if you write in the meters, 0.01 meters. So induced EMF E is equal to minus 15.7. With the integral of dz is a Z. Upper limit is a 0.01. 0.01 means 1/100. 1/100 means again it is a 15.7 by the 100 means 1570 millivolts, or we can take it as 157.0 millivolts. Therefore, the E is equal to, we got as E is equal to minus 157. If I write it is a 157 means pi 10 is there. And here the 0.01, you'll get the pi 100. 100 into 10 is a pi 1000. Pi 1000 is actually is a volts. Okay, my dear students. Therefore, the E is equal to now it becomes of minus 157,000. You'll get it in the numerator, 10 power minus, so millivolts. So induced EMF or the induced voltage, if the radial field is given by the B bar is equal to 0.5 R bar Tesla, is E is equal to minus 157 millivolts we got. Okay, my dear students. Let's see here. Same thing, what we got, the E bar is equal to the induced EMF, E is equal to minus 157.08 millivolts. 157.08 millivolts. Okay, my dear students. Coming to the next example, itself, a circular loop lies in a plane Z is equal to 0. So lies in a plane Z is equal to 0. So it shows in the Z is equal to 0 plane and has a radius of 0.1 meters and has a radius of 0.1 meters and resistance of 5 ohms. Given the B bar is equal to 0.2 sine 10 power 3 t. Here it is a T given, AZ bar. Determine the current in the loop. Determine the current in the loop. We need to find the current here for the given data. What is the data given? The resistance is given as a 5 ohms and B is also given 0.2 sine 10 power 3 t AZ bar. Okay, and they are asking to find the current in the loop. So what is the formula for the to find the current in a loop? Let us first of all calculate the induced EMF. The circular loop is in the Z is equal to 0 plane. B bar is in the Z direction, which is perpendicular to the loop. So the B bar is perpendicular to the circular loop. The total flux is given by phi is equal to integral B bar dot ds bar. You know the phi is equal to integral B bar dot ds bar. What is a B bar? It is along the Z axis. And ds bar is also can take in the along the Z axis. Since it is in the cylindrical coordinate system, R, phi and the Z along the Z axis, ds Z bar is equal to differential surface area normal to the Z direction is dr R into d phi AZ bar. Okay. That is equal to phi is equal to the integral. What is the B bar given? 0.2 sine 10 cube into t AZ bar dot is a one term dot R into dr dt d phi. It is also AZ bar. Okay. Now AZ bar dot AZ bar is equal to 1 and phi, the induced total flux is phi is equal to dr and the d phi, the 0.2 integral R sine 10 cube into t dr d phi. And here, with respect to the R and with respect to the phi, the remaining terms all it is a constant. So you can write this as a 0.2 sine 10 cube into t is a constant. Integral R dr integral d phi. The phi is varies from the 0 to 2 pi. You already know. And the radius is given. What is the radius radius is a 0.1 meters up to the 0.1 meters. So you can take the R is equal to 0 to 0.1. That is equal to 0.2 sine 10 cube into t, or integral R is R square by 2. R square by 2 with upper limit is the 0.1. Lower limit is a 0. And d phi is a 5. Integral d phi is a 5. Upper limit is a 2 pi. Lower limit is a 0. That is equal to 0.2 sine 10 cube into t, and 0.1 square by 2 is a 0.1 square by 2 and into 2 pi. The upper limit here the 2 pi. That is equal to the above value we have 0.2 pi, 0.2 into 0.1 whole square is also there, 0.2 pi, 0.1 whole square into sine 10 cube into t. So this is a value we got to the total flux. Phi is to, if it is a phi is we can write as a 3.14 multiply with the 0.2 and the 0.1 whole square also. It is a 0.01. 0.1 whole square, you'll get the 0.01 into 0.2 and 0.5. 0.2 pi, we can multiply. The coefficient will get as a sine 10 cube into t. Okay. That is a meter Weber. Got it, my dear students? But they are asking that determine the current in the loop. Got it, my dear students? The induced EMF, the E is equal to d phi by dt. D phi by dt. You can apply the with respect to the t for this term. The value is here. .2 pi and is a 0.1 whole square sine 10 cube into t by the dt. It's a d of by dt with respect to the t we are applying. So the E is equal to, we got as 0.2 into 0.01. Okay. Into sine 10 cube. Sine 10 cube into t only, you can apply the derivative d by dt of sine 10 cube into t. What is the sine derivative? The cos. You can write that cos here. 0.2, if you write, it is a pi also there. Pi into 2 by 0.2, if I am writing as a 2 by 10. 0.01, if I am writing it as a 1 by 100. 1 by 100 into pi. Now, what is the derivative of sine 10 cube into t? It's a cos 10 cube into t. And again, the coefficient of t is there. That is a 10 cube. Got it, my dear students? That is E is equal to, we got cos 10 cube into T into the T coefficient is a 10 cube. See here the 10 is there and the 100, nothing but the 10 cube only. You can get cancelled this function. And the E is equal to now the 2 pi into cos 10 cube into T. Is a E value we got. Is a volts. Got it, my dear students? What is it? 2 into pi? Pi is equal to 3.14, and you can multiply the E is equal to 4 is a pi cos 10 cube into T. Therefore, E is equal to, you can multiply with it. 2 2s 2, 2 1s 2, 2 3s is 6.28 cos 10 cube. You got that? Find out the current in the conductor is given by the I is equal to, what is I now? Always I is equal to induced EMF by the resistance, because it is the resistance is given induced EMF E by the resistance R. Substitute the induced EMF here as 6 point, here the cos derivative of sign is a minus cos, minus, and here the minus, and here also the minus, and it is a minus. So minus 6.28 cos 10 cube into T by the resistance is given. What is the resistance is given? The 5 ohms. Resistance is given the 5 ohms. Got it, my students? Therefore, the current I is equal to, the minus, you can calculate 1.2, and it is a 1.25 will get minus 1 point approximately. I'm writing 1.25 cos 10 cube into T. Okay, it is a current is amperes. Got it, my students? Therefore, for the given data, a circular loop conductor lies in plane Z is equal to 0, has a radius of 0.1 meters, and the resistance of 5 ohms given with the B bar is equal to 0.2 sine 10 cube into TAZ bar. Determine the current in the loop. So first of all, we take that is a phi is equal to B bar dot DS bar to find the induced EMF by taking the derivative with respect to the T. Then you can substitute I is equal to E by R. So we know the V is equal to IR. The formula is the voltage V is equal to I into R. So I is equal to V by R. That V is in the induced EMF. We can take the change of the flux with respect to the time, d phi by the dt. The next example. In a given lossy dielectric medium, conduction current density JC is given, ampere per meter square, that is 0.02 sine 10 power 9 into T. Find the displacement current, JD they are asking, if the sigma is equal to 10 cube, and epsilon r is equal to 6.5. So we know the lossy dielectric medium, the JC bar, the magnitude of JC bar by the magnitude of JD bar is equal to sigma by the omega epsilon. This is a formula we have. Then we need it is a JD, displacement current density, as of omega epsilon, the JC divided by the sigma. So cross multiply here JC into omega epsilon and get this sigma is the denominator. What is the omega here? Omega epsilon, and epsilon is in the epsilon naught and epsilon r, and JC whole divided by the sigma, whole divided by the sigma. And then saying that it is a magnitude of JD bar here, and here also the JD bar, JC bar. And omega, what is the omega here? Sine omega t. This is a function of a sine omega t. JC is equal to the given. Here it is a 0.02 is a magnitude of JC and sine omega t. That is nothing but is ampere per meter square. What is the omega here? 10 power 9. You can write that is a 10 power 9 into epsilon naught. We know the 8.854 into 10 power of minus 12 is a constant value, my students. And epsilon r is there given into 6.5. And here there is a magnitude of JC. Magnitude of JC. What is the magnitude of JC? Here the 0.02. And substitute here the 0.02. Whole divided by the sigma. What is the sigma given? 10 power 3. The conductivity 10 power 3. So here the 10 power 3 and here the 10 power 9 is a 10 power 6. Got it, Madam? And further you can simplify this, multiply the function. 6.5 is a 65 by 10 and the 2 by 10, 2 by 100. You'll get again the denominator is a 10 power 3. And here is also 8.854 means here the 10 power 3. So 10 power 3 and 10 power 3 you get it is a cancel of 10 power 6 also. And you can multiply, or finally we got the JD is equal to 1.15 into 10 power of minus 6. Okay, it is a microampere per meter square. And now these are only the magnitude, my students. We got the magnitude. Then JD bar is equal to. JD bar is equal to, if it is in the sine function, and now it is in the JD is the cos function. Conduction current density and it is a displacement current density. Its a magnitude is a 1.154 of minus 6. Take the magnitude 1.15 and the same you can write as a JD is equal to the magnitude of JD and cos omega t ampere per meter square. Its a magnitude is a 1.151 cos omega is a 10 power 9 into t. We got is a 10 power minus 6 is also there. You can write that as a microampere per meter square. Microampere per meter square. Got it, my students? Coming to the next example. If the magnetic field H bar is equal to, if the magnetic field H bar is equal to 3x cos beta plus 6y sin alpha AZ bar Find the current density J bar. Find the current density J bar if the fields are invariant with the time. See, one of the Maxwell's equation we know there's a modified Ampere circuit law. Del cross H bar is equal to JC bar plus JD bar. That JC is the conduction current density. You can write as a J, and JD is a dou D bar by dou T, displacement current density. Given that is a H bar is equal. Okay, but as a fields or current are time variant, we can write as a dou D bar by dou T is equal to 0. Okay, it's a time invariant. The fields are the time invariant. The term, whatever we have, it is with respect to the time is a value is a 0. So del cross H bar is equal to J bar. That J bar is a conduction current density only. And they're asking the current density J bar only. The del cross H bar you have to find out. Therefore, the J bar is equal to del cross H bar. Del, it is in the Cartesian coordinate system, AX bar, AY bar, and AZ bar. Del is a dou by dou X, dou by dou Y, and the dou by dou Z. And what is the term here? We have AZ bar term only. There is no X and there is no Y, and only we have Z coefficient 3x cos beta plus 6y sin alpha. Got it? So now you get the J bar is equal to, if you take the AX bar coefficient, dou by dou Y of this function, dou by dou Y of 3x cos beta plus 6y sin alpha minus this term is a 0, and AX minus AY bar coefficient is a AX bar coefficient, my dear friend. So minus, and AY bar again it is a dou by dou X of dou by dou X of 3x cos beta plus 6y sin alpha into AY bar. And coming to the AZ bar, both the terms is a 0. There is no AZ bar coefficient. Now apply here the dou by dou Y. The first term is a 0 because it's a constant. There is no any Y term. And here 6y sin alpha, dou by dou Y is 6 sin alpha. 6 sin alpha AX bar, and minus dou by dou X. For the second term, there is no X term. Second term is a 0. And this is becomes of 3 cos beta AY bar. Therefore, the J bar is equal to, it's ampere per meter square. Current density 6 sin alpha is X bar minus 3 cos beta AY bar. Got it, my dear?